Hello, everyone. For the sake of time and the famous promptness of time of Japanese, I'd like to start this afternoon session of keynote speeches commemorating the first joint meeting between the Japan Geoscience Union and the American Geophysical Union. My name is Kiyoshi Suehiro, and I'll be moderating this session on behalf of the two unions. This session has two very distinguished talks, and we'll have each talk to be introduced by the presidents of the two unions. The first speaker is Dr. Lucy Jones, and the second speaker is Professor Takaaki Kajita. And the time allotted will be split into half. So without much further ado, I would like to call first upon the president of the American Geophysical Union, Eric Davidson, to introduce the first keynote speaker, Lucy Jones.
Thank you. It's my honor and privilege to be able to introduce Dr. Lucy Jones today. As with most introductions, would start with her academic background, and this is a very interesting one, and that she has a Bachelor of Arts in Chinese Language and Literature from Brown University, and then obviously went from there quite linearly to a PhD in geophysics from Massachusetts Institute of Technology. She completed 33 years of service with the US Geological Survey and was very active in earthquake research for many decades. She furthered earthquake risk reduction through seismological research and integrated disaster scenarios, and is a renowned expert in the field of earthquake foreshocks. At the USGS, she was science advisor for risk reduction, leading the long-term science planning for natural hazards research. She created the science application for risk reduction that applies USGS science to reduce risk in communities. She developed the Great Shakeout, which has expanded to encompass 55 million participants around the world. She led the creation of a national science strategy for all the natural hazards studied by the US Geological Survey. And now she is the founder of the Dr. Lucy Jones Center for Science and Society, whose mission is fostering the understanding and application of scientific information in the creation of more resilient communities. The center works with the public and private sectors to increase communities' ability to adapt and be resilient to the dynamic changes of the world around them. The center helps scientists become better communicators, something we very much need in these days, and helps decision makers understand how they can partner with scientists to make better informed decisions, also something we urgently need, especially on the other side of the Pacific at this moment. She's a dedicated science communicator, as you will find. She is frequently interviewed on television and newspapers, where she is very well known as the Earthquake Lady. But today, I'm happy to introduce her to you as Dr. Lucy Jones.
Thank you, Eric, and thank you to everyone for being here. I'm very happy to be back in Japan, where seismology began, and hoping I'll feel at least one earthquake while I'm here, and envying your seismologists for just how much data you have to work with. The last time, my last trip to Japan was at the invitation of a group called Women's Eye, which is a Japanese NPO, nonprofit organization, created to support the women of Tohoku as they work to rebuild their communities after the great East Japan earthquake and tsunami of 3/11. These women are trying to create new businesses to support themselves and their community, often in an environment that is skeptical of working women. Women's Eye invited me to participate in their grassroots academy, partly as a role model of a professional woman who has survived an active career while raising a family. They took me to Iwate, one of the most beautiful places I think I've ever seen, where I could see firsthand the devastation that was wrought by the 3/11 disaster. I am a seismologist. I know what an earthquake is. I know what a tsunami can do. But what I learned in Iwate and Miyagi was the human toll, what it means to be in communities where everything was destroyed, communities that lost 10% of their people, where you know hundreds of people who have died, what it means to live in temporary housing for 5 years or more, to wait to have a home that cannot be where it was before, what it means to struggle with recovery years after the world has stopped noticing what happens to you. Women's Eye helped me understand how much our societies have in common as we learn to live with the risk of natural disasters. I live in California, and in the northern part of the state, we also have a subduction zone and the risk of large tsunamis. The town of Crescent City has a history of damage and life loss from tsunamis. 2 years after the 3/11 disaster, a boat washed up in Crescent City, covered in barnacles. A friend of mine there, Professor Lori Dengler, was asked to investigate. They realized the boat had come from Japan in the tsunami, and they were able to determine that the boat belonged to Takata High School in Rikuzen, Takata. Not only were they able to return the boat to Takata High School, but Takata has formed a sister school relationship with the high school in Crescent City. Students have visited back and forth. The Californians now have a better understanding of the risk they face and what to do about it. Lori wrote a book, a children's book, about this boat that is published with both languages. I brought a copy of the book with me to give as a gift to my Women's Eye hosts. We discovered that one of the women at the academy was a graduate of Takata High School, and she had sailed in that boat when she was a student. From across the ocean, the disaster can connect us, and I gave the book to her instead of to my hosts. I also discovered just how much the residents of Iwate, like the residents of California, want to understand the risks that they face. I was brought to Iwate to discuss women's careers, but I spent many hours explaining aftershocks and Amore's law and attenuation relationships. These Japanese women who had lost so much wanted to understand why. Understanding why something happens makes it less scary. I was also taken to Otsuchi, where the city hall, as you see here, sat behind a 6-meter seawall. When the prediction was issued for a 5-meter tsunami, the city leaders ignored protocol that said to move to higher ground and conducted their emergency meeting in the city hall. When the tsunami poured over the seawall, they lost over 1,000 people, including most of their city government. The woman who gave me a tour asked me to begin by entering this shrine constructed in front of the City Hall, and to pray for the victims. Because, as she said, we need to remember why we are doing this. This is where I want to begin this talk as well. I want us to remember the victims. Remember that society wants our help, needs our help, to save people's lives and their livelihoods. I am not proposing that every piece of research needs to have a concrete benefit. I am saying that as a scientific community, I believe we should, as a moral duty, be fostering the creation of information that can be used to make a safer society and ensuring that that science is used. So, what does society want from us? A separate question is, what does society need from us? They are not the same thing. And what can we give them? That's a third question. What is the intersection of what they want, what they need, and what we can provide? Another question altogether. I think we can all agree that most people want, more than anything, for us to tell them when a disaster will happen. I would guess that many of us have had the same experience. You tell a new acquaintance that you are an earthquake scientist, and their first question is, when will the next earthquake be? Or perhaps, is the big one going to happen soon? In seismology, we have spent a great deal of energy discussing earthquake prediction. Is it possible? How much effort should be directed towards it versus other activities? But I'd like to suggest that we can also gain some insight by considering why people want prediction. This has as much to do with emotional needs as practical considerations. Human beings hate randomness. Let me explain. The social sciences have important information for us about how human beings perceive risk. We evolved our ability to reason, not to solve equations or conduct scientific research. We evolved our reasoning ability to survive. In our early world, our brains were our tool and defense against the much larger muscles and teeth of the predators who saw us as a tasty treat for dinner. And in that world, a peril that was unseen was much more difficult to avoid. Professor Paul Slovic is a psychologist at the University of Oregon. He has studied what makes people more fearful. He found that there are several factors that make a peril more frightening. Three of the biggest ones are something that cannot be seen, something that is very uncertain, and something that seems unknowable. All of these trigger our primal fears of the unseen predator hiding in the jungle. We have literally evolved to be afraid of randomness. So we respond by trying to find the pattern. We evolved to find these patterns to infer that waves in the grass means a predator in hiding. We find patterns even when they're not real. We see constellations in the stars. When there is no pattern, we still try to make one. And when, in fact, the underlying phenomena is random, we often find it necessary to create a pattern with an escape hatch, something that cannot be tested and therefore will last through repeated examples of randomness. Traditionally, most cultures have put the pattern in the spiritual realm because we can claim the pattern is there, but we just can't see it. In the West, where the culture prizes individual action, the Christian tradition was that God was punishing sinners. After the 1755 Lisbon earthquake, which happened on a major religious holiday when everybody was in church, the Dutch government, which were the Protestant Christians, refused to send aid to the Portuguese government, the Catholic Christians, saying, God has decided how much the people of Lisbon should suffer, and it is not our place to change what God has decreed. They knew that that's why the earthquake had happened right when the churches could collapse on the people. In the East, where social harmony is the overriding good, earthquakes were seen as the result of a disruption of the yin-yang balance. A benevolent government would demonstrate its cosmic rightness by a lack of natural disasters. But when there was divergence between cosmic moral principles and the state of government increased, disasters, especially earthquakes, became the concrete manifestation of cosmic displeasure. The development of science in the last 2 centuries has displaced much of this old way of thinking, but rather than accepting the randomness, many people now turn to the scientists to remove the randomness, to make predictions. I would suggest that much of the desire for predictions is the search for something to assuage our fear of the random. The public is asking the seismologist to serve the same function as the priests used to serve, to give a reason for the disaster and remove the randomness. And we scientists are human beings. We like patterns probably more than most people, and the search for patterns seems like a reasonable endeavor. I spent much of my career trying to find patterns in the temporal distribution of earthquakes. Early in my career, as you heard, with a Chinese degree and being in geophysics, I had the opportunity to study the 1975 Haicheng earthquake and foreshocks. I was actually the first American scientist to go to China when relations between the 2 countries, China and the US, was normalized in 1979 while I was still a graduate student. This earthquake was predicted, saving lives. It was not as formal a government activity as we thought, but people really were evacuated from many buildings before it struck. And I would recommend Kulin Wang's excellent paper if you want to know more. My research was specifically directed at trying to understand what had happened at Haicheng. How had they predicted that earthquake? Part of the answer, a large part of course, is that the earthquake had over 500 foreshocks, most of them in the 24 hours before the main shock. But the prediction did not happen because the Chinese knew more than we do about foreshocks. They used the basic principle that Omori Sensei quantified more than a century ago. One earthquake makes another earthquake more likely, and guessed that having a swarm of over 500 events made a big earthquake even more likely. And then because of the political and economic system in China in 1975, they could act more aggressively on a low probability situation. They had more to gain from a prediction because of the poor building stock and less to lose from a false alarm. In other words, the decision to act on a set of scientific information was made because of social, political, and economic factors. I looked at this situation and decided to focus on determining a probability that some sequence of earthquakes would be followed by a large earthquake. I thought I could encapsulate this seismologic information about the situation into a probability and hand it to the person who had the social and economic information, and most importantly, the societal responsibility to make a decision of how to act. It really didn't work. So we made fancier graphics and automated systems, and it still has basically been ignored. With many, many years of perspective, I have again turned to the social sciences to understand why our attempts at communicating with probabilities have not led to actions that would make our societies safer. The most important insight is that people do not make decisions in probabilities. Whatever information we give them, they have to make a decision to act or not act. The probabilities have to collapse to 1 or 0, act or not act. The decision is made using much more information than just the probabilities, but not the quantifiable analysis of economic costs and consequences that I had imagined. Social science shows us that when strong emotions are involved, people tend to focus on the badness of the outcome rather than on the probability that the outcome will occur. They call this probability neglect, and it helps to explain excessive reactions to low probability risks of catastrophe. Sometimes it also goes the opposite way, and people ignore what is a relatively high probability situation. Why? Well, the main thing is we fool ourselves into thinking that we are more rational than we actually are. Let's go back to the idea of the evolution of human reasoning. We did not evolve our brains to search for truth and meaning. We evolved our brains not just to survive against predators, but to do so in the hypersocial setting of a tribe of early humans. We needed to be able to make sure that we weren't out in danger hunting for the next meal while someone else stayed in safety back in the cave. Our reasoning ability evolved to win arguments. And to win an argument, you don't have to be right, you have to be convincing. So we've come to realize that all human beings tend to what is called a confirmation bias. We are less critical of information that confirms our pre-existing viewpoint and more critical of information that confounds it. This means that people will respond to information like probabilities, believing that they are making a rational decision for logical reasons, but in fact, they are probably acting in confirmation of a viewpoint they already held. We tell ourselves we are right. We are our own internal yes man. And scientists should not smugly believe that it's only other people who suffer from a confirmation bias. You know, the policymakers, the responsive officials, but not us. In fact, research shows that people who believe that data matter, and that probably describes most scientists, are the more susceptible to a confirmation bias. This is why we have peer review. We know that the easiest person to fool is oneself. None of us like peer review, but we know it is necessary. We must also be vigilant about the trap of a confirmation bias and how we present our hazards work to policymakers, and especially vigilant when sharing a confirmation bias means that peer review is not effective. The most obvious American example of this is probably the Parkfield earthquake prediction experiment. We used statistics that said the earthquake had a 95% chance of happening no later than 1993. But those statistics were only true if our model was 100% correct, which it wasn't. And the earthquake actually happened in 2004. Our shared confirmation bias led us to believe we saw a pattern. So when we do this, we need to ask ourselves, is our model better than a random distribution? We develop models because we believe they are right. However, as scientists, we also know we have to hold out the possibility that they're wrong. The question is, what should be our standard for asking others to act on our model? Because there will be costs. It is the policymaker's job to determine if the costs are reasonable to the benefit, but it is our job to do everything we can to make sure the information is correct. How do we protect against our own confirmation bias costing others for no reason? Well, this is why we have statistics. This is probabilities used for scientific validation. Can you demonstrate that your model does better than assuming it is random? I believe that we should not ask policymakers to act on our information if we cannot demonstrate that we have more information than a random distribution. I once said this at a workshop, and a very famous geophysicist, who I won't name, replied, "But if we insist on being able to demonstrate it's better than random, we'll not have anything to say." I replied by just looking at him. That's sort of the point. And I just missed some of my things. We have gotten into the trap of probabilities, or at least I did, because it seemed the closest approximation to what people wanted from us. They asked for deterministic predictions. We couldn't give them that, so this seemed the closest approximation. But when probabilities are ignored or misused, what's next? Let's step back from it trying to find the closest approximation to what they want and try to ask what they need, and how does that interact with what we can say. To do this, I'm going to turn to a much more recent part of my career. In 2014, I spent a year in the mayor's office in the city of Los Angeles, working with his staff to develop a comprehensive program for increasing the seismic resilience to the city. It was a year-long experiment to understand what information was most useful, but also what was the information that made the connection with people and inspired them to act. This program was almost unbelievably successful. I still look back in surprise. The city committed to requiring owners to retrofit almost 20,000 dangerous buildings, and the owners agreed to pay for it without fighting the new law. The lawmakers voted unanimously to pass it. And now, a year and a half since the law was passed, over 1,000 buildings have already begun the work, and more are getting in the stream. The city also committed to remaking their water system. We know the lack of water after an earthquake is one of the most dangerous things we face. They are struggling to find the money, but every new project in the municipal water system is reviewed for seismic resilience. They have begun prioritizing the pipes for upgrade to seismic-resistant pipes. A new project has been created to create a Lifelines Council for Southern California to strengthen the electric system and other utilities, especially where they cross each other coming across the mountains. The lifelines have to be close together in the mountain passes, and this is also where they cross the San Andreas Fault. The utilities are now working together to find solutions. And now the new ideas are starting to go to the 191 other cities of Southern California beyond Los Angeles. I've been working with the Southern California Association of Governments to help other cities move forward. 2 other cities have also passed retrofitting legislation, and more than 10 others are starting the process. All told, it has been the largest single increase to seismic safety that we have ever seen in California. One of the most difficult things to do is to analyze oneself. but I want to look back and try to understand what made this project successful. This turned out to be information that was needed and was used, and if we can understand why, this might give us some insight as to how we can help society in the future. First, we began from the shakeout scenario. This scenario of a plausible magnitude 7.8 earthquake details the consequences of an earthquake on the southern San Andreas Fault, the fault most likely to produce a great earthquake in the conterminous United States. The scenario is itself a synthesis of research conducted for decades to understand the earthquake hazards and risk in Southern California. Earthquakes on faults closer to the city will cause more intense damage in parts of Los Angeles, but this very likely San Andreas Fault earthquake happens over a larger area and strains our regional capabilities through the sheer scale of the damage. It is our Kanto earthquake. The scenario predicted huge financial losses. Because the randomness of earthquake triggers our primal insecurities, California has primarily addressed earthquakes as a problem of life safety. The philosophy of the building code is that the financial decision of how much to invest in a building's strength is an individual owner's decision to make, and they have the right to choose a building so weak that it is a complete financial loss after the earthquake, as long as they do not kill someone in the process. The result is an urban environment designed to be a financial catastrophe in the expected predictable future earthquakes. When the biggest earthquakes occur, we face a potentially even greater loss from depression to the regional economy. A long-term depression damaged San Francisco after the Great San Andreas earthquake of 1906. In 1905, San Francisco was the 6th largest city in the United States, with a population of 400,000. Over the next 2 decades, as other American cities grew several-fold, San Francisco lost population at first and then had only limited growth. The greatest growth in the history of Los Angeles was the decade after 1906, as people abandoned San Francisco and moved south. This approach of basing the discussion on a discrete scenario accomplished several psychological objectives that I think made the project more successful. First, a scenario is a story, a narrative of what the big earthquake will be like that allows people to connect emotionally to the consequences. As scientists, we know that stories mislead us. Anecdotes are a good way to get the wrong answer. But human beings make decisions through emotional connections. The process of creating a scenario is a way to get scientists to agree that an outcome is plausible. It is a process to create a scientifically defensible story and bridge this divide between scientists and users. By using one concrete event, I avoided discussion of probabilities. I just said it's likely enough to be worth preparing for. When we focus on probabilities, we focus on what we don't know. Remember that the psychologists tell us that uncertain things are more frightening. Something that is frightening and uncertain is something we would like to ignore. As scientists, we know that uncertainties matter, and to convince our colleagues of our results, we need to demonstrate that we have analyzed and understand the uncertainties. Scientists and engineers are probably the only people in the world that like uncertainty. Policymakers need answers. They rely on hearing a consensus from the scientists to know that we have done our job. So results are the most effective when you can demonstrate that they are the consensus of the scientific community, and then you give the results and not the process by which the scientists achieved the results. By emphasizing the financial aspects, I moved people away from fear that can paralyze decision-making, looking at the finances instead of losing your life. I showed them that they were going to have to pay for the earthquake one way or another, either now or after it happens. It was just a matter of when. We also focused on how our vulnerability is shared, that someone's decision not to be ready increases the chances that others will suffer. So that's the scenario approach. The second thing I realized was important was to keep clear the boundary between science and policy, even as the policymakers and scientists worked in close collaboration. As a scientist, I can give the policymakers a prediction of the probable consequences of their decisions. As a citizen and voter, I have an opinion as to the appropriate policy to respond to that information, but that is not part of the science. We elect our policymakers to choose the policy, and that should not be the scientist's job. This is important for two reasons. First, if the scientists start making policy, we are inviting the politicians to start making science. Second, the policymakers fight for the policies that they have made. So by empowering them with the information to make more informed decisions, we also create more successful advocates in the people who actually have the power to get something done. Third, as I just said, everyone supports something they helped to create. So engaging stakeholders in the discussion from the beginning is really a condition for success. Most of my year at City Hall was spent in meetings like this one, talking about the science, but also listening for ideas. Many of the details of the proposals came from people who will be affected by the plan and who could have formed impossible barriers to its enactment. Being able to affect some piece of the plan gave them a stake in its success. And lastly, I want to say that relationships matter. The city of Los Angeles did not suddenly decide to listen to the scientists. This collaboration is the culmination of decades of interactions, especially the closer collaboration that developed out of the shakeout scenario process. For the last 7 years, many scientists have been engaged in close collaboration with emergency managers, utility engineers, and regional officials. With the now annual shakeout drill, the message about earthquakes is being heard on a more regular basis, and it is connected to the credibility of the scientific analysis. It is not just the credibility of the science, which has always been there, but the relationship with the scientists. People listen to people they trust, and that trust comes from familiarity and shared experience. I want to finish where I began by thinking of the victims and what obligation we as scientists have to communicate the information we have discovered. To try to think about this, I would offer an analogy. If we see someone standing in a road where cars travel at high speed, and we see a car coming that they don't notice, what should we do? If it's a young child, a moral person will remove the child because they don't know better to do it on their own. If it's an adult, we make sure they know the car is coming and trust them to make their own decisions. But when we tell them a car is coming, we need to say, hey, a car is coming. It's likely to hit you. We don't say, hey, force equals mass times acceleration. That may be the relative science, but it is not useful at that moment. We need to make sure that our warning can be understood and acted on. So that moral decision is pretty straightforward. How do we think about it as Earth scientists? It means, I believe, that we have an obligation to create information products that are usable by decision makers. What that means is that we need to focus on what we know, not on what we don't know. We need to spend time to develop relationships, work with decision makers so they understand the implications of their decisions, but not presume to take their decisions from them. We also need to recognize that people make decisions because they have emotional connections to the problem. They make decisions based on stories. As scientists, we've learned to reject stories as misleading, but we need to accept that the transmittal of the information needs a story. We need to create scientifically defensible stories because our world is connected and we are all in this together. Thank you.
Thank you very much, Lucy.
Thank you.
Perfect timing.
Okay, good.
So I'd like to move on because the time is almost here for the second talk. I would now like to call upon Professor Hodaka Kawahata, the president of the Japan Geoscience Union, to introduce our second distinguished lecturer, Takaaki Kajita, the Nobel laureate in physics.
Yeah. Thank you for the chairman. I'm Hodaka Kawahata, the president of the JpGU. With great honor and pleasure, I would like to welcome all of you to this keynote speech hosted by the two unions. The mission of the JpGU is to promote science, and we believe that making the opportunity to have the high-quality lectures is one of the key to the success of this meeting. So we decided to ask the prominent scientists to give their lectures at this memorable first joint meeting. At the basic tone for the development of the science. I am sure that everybody is looking forward to these lectures. Now I would like to introduce you today's guest speaker, Professor Takaaki Kajita. He is the special university professor at the University of Tokyo and also the director of the Institute for Cosmic Ray Research at the University of Tokyo. Professor Kajita received the PhD from the School of Science, the University of Tokyo, in 1986, and has been researching at Kamiokande and Super Kamiokande detectors at the Kamioka observatories in central Japan. Both Kamiokande and Super Kamiokande are Neutrino observatories located within and around the former Kamioka mining near the city of the Hita, Gifu Prefecture, Japan. In 2015, he shared the Nobel Prize in Physics for his role in discovering the atmospheric neutrino oscillations. Currently, he is also the project leader of the Kangura. This Kamioka mining is famous for the formation of the process of the skarn type deposit. In skarn type deposit, the hydrothermal solutions react with the limestones, whose chemical composition is calcium CO3, resulting in the formation of secondary minerals and heavy metal precipitations. It has been producing the lead, zinc, silver for the more than 1,000 years. Its operation started around 720 AD and ended 2001. At a certain period in histories, this mining was the largest in Oriental countries. He will be talking us today on the topic of exploring the universe. with neutrinos, gravitational waves, and gamma rays. Please join me in welcoming the Kajita sensei to this stage.
Oh. Strange. Okay. Okay, can I begin? Yes, I hope so. Okay, good afternoon. First of all, thank you very much for the kind introduction. And well, it's an honor for me to speak in this JpGU-AGU Joint Meeting 2017. So today, I'm going to talk about exploring the universe with neutrinos, gravitational waves, and gamma rays. Well, actually, in more detail, well, this is the outline of this talk. I have a brief introduction of this talk. Then, well, I'm talking about the neutrinos, gamma rays, and gravitational waves. And, well, actually, before starting this talk, I think I have to apologize. Although the title of this talk is, I don't know. Well, maybe this doesn't have enough power, so let me try to improve. HDMI あります？電源もそうそうつなごうと思います。Okay, good. Well, I think I was in the middle of my apology. Well, yeah, actually, well, the title is very general, but well, what I'm going to talk today is mostly, well, the introduction of the activities in the Japanese community. So, therefore, So this is my apology, and I want to start. Well, so now we are very actively exploring the universe, but, well, people have been interested in the universe even, say, 1,000 years ago. Well, this is a famous diary called Meigetsuki, written by Fujiwara Teika. And this is one page of his diary. And in this page, there is a description of something new in the universe. In fact, the yellow part told us that this is a description of a very bright new star that appeared on May 1st, 1006. The second one, the green one, shows the description of a bright star that appeared in May 1054. So it's clear that, well, we have been interested in the universe for a long time. Now, well, I want to talk about more recent story. That was about 100 years ago. Victor Hess had a measurement of the radioactivity. He measured the radioactivity as a function of the altitude. He himself went to a very high altitude with this balloon. And, well, you may have no idea why he had to do this. Well, in fact, at the beginning of the 20th century, people noticed at the ground level there is a natural radioactivity. And people believed that this radioactivity is coming from the Earth, ground. If this assumption is correct, then if he goes up to the very high altitude, the radiation should be decreased. So he tried to measure the radiation level at the high altitude, and he found that the radiation increases with the altitude. So this was clear that radiation was coming from the space. And this was the discovery of the cosmic ray. So this tells us that there are phenomena in the universe that cannot be observed with optical telescopes. Also, scientifically, this observation asked us where and how these particles are accelerated. Okay, well, these 2 pages are my introduction. And in fact, the previous page and this page might be related or connected. That is the topic in this talk. Now, first, I want to talk about the exploring the universe with neutrinos. This page tells you the life of a star. If a mass of the star is small, mass of the star is, yes, okay. Then the life is very long. If the star is a little bit more massive, say something like our sun, then their life could be around 10 billion years. And at the end, they become red giant, and at the end, there will be a white dwarf remaining. If a star is even more massive, say 10 times the mass of our sun, then their life is rather short, and at the end, they become super giant, super red giant, and explorer at the end. And that is the supernova, and after the supernova, neutron star will be remaining at the center. If the star is even more massive, after the supernova, maybe a black hole is formed. So this is our basic understanding of the life of a star. And in fact, about 30 years ago, we saw a supernova at the Large Magellanic Cloud. These two are the photos of the Large Magellanic Cloud before and after the supernova explosion. You can see a very bright star after the explosion. And at that time, a neutrino detector called Kamiokande and also IMB experiments were in operation. And this is the data taken at that time by the Kamiokande experiment. Here, we show the data points as a function of time, and the vertical axis is the event energy. And you can see at time around 0, there are clusters of events above backgrounds. And this was the observation of supernova neutrinos. And the number of events we observed during that time was about 20, including all the events observed in Kamiokande, IMB, and Baksan experiments. But anyway, only these 20 was enough to understand the basic mechanism of the supernova explosion. Therefore, Professor Koshiba received the Nobel Prize in Physics. But, of course, 30 years ago, the number of events we were able to observe was about 20. That was not enough to understand the details of the supernova explosion. So we hope to observe the next supernova sometime soon. Therefore, in Super Kamiokande, which is about 20 times larger than the Kamiokande experiment, is waiting for the next supernova. Well, unfortunately, we have been waiting for 20 years, but we were unable to observe any supernova. So today, I can only just show you what we expect for a supernova observation in Super Kamiokande. Okay, so this is the video produced by our Duke collaborator. So this is Super Kamiokande. And well, this is noise. So soon, yes. So, well, maybe about 10 seconds. There are lots of events, but after 10 seconds, well, we come back to the noise level. So this is what we expect to observe. But, well, actually, in this video, in order for you to understand what's going on, the number of events was substantially reduced. If a supernova explodes at the center of the Milky Way, Super Kamiokande should detect about 10,000 neutrino events in 10 seconds. So with this, with this large number of events, we would like to understand the mechanism of the supernova explosion in detail. But as I said, we have been waiting. And people say that the expected supernova rate in our Milky Way would be around 1 or maybe 2 per century. So maybe we have to wait for another 80 years. That could be a little bit too much. So Super K is now thinking another way of observing supernova neutrinos. Well, this is the image of the universe. The left is the birth of the universe, and well, time goes to the right, and we are at the right side. And, well, of course, in the history of the universe, there have been a lot of supernova explosions. And in each of these supernova explosions, a substantial number of neutrinos have been emitted, and they are propagating in the universe even today. Therefore, Super Kamiokande collaboration would like to observe neutrinos produced by the supernova explosion in the past universe. In this way, we'd like to understand the supernova rate in the past history of the universe. And in fact, well, the present Super Kamiokande is not powerful enough for this measurement. Therefore, Super Kamiokande plans to improve the detector probably next year, or maybe 2 years later. Anyway, soon Super Kamiokande would like to modify the detector so that Super Kamiokande is sensitive to the past supernova neutrinos. Now, I want to move on to the second topic, that is the exploring the universe with gamma rays. Well, I introduced the record about 1,000 years ago. Now, you may ask, what is the present image of these new bright stars 1,000 years ago? Well, in fact, these are the present images of the supernova that happened 1,000 years ago. So, well, okay, these are rather, say, beautiful images. And we think that these supernova remnants are the sources of cosmic rays, or at least as part of the sources of cosmic rays. So, we would like to know if these are really the source of the cosmic rays. Now, here is the source, and here is the Earth. If a cosmic ray is produced at the source, then they have to propagate in our galaxy, but our galaxy has some magnetic field. Therefore, if a cosmic ray is generated at the source, and they could come to the Earth, but even if we have a very precise measurement of the cosmic ray at the Earth, we have no idea where the cosmic rays are generated. That was the problem in understanding the cosmic rays. Then what shall we do? Well, we have to measure gamma rays. Cosmic rays produced at the source may interact with the surrounding matter, then gamma rays are produced. And gamma rays, of course, do not feel the magnetic field. Therefore, they come straight to the Earth. That way, if we observe gamma rays, we could understand the sources of the cosmic rays. Oh, by the way, I just want to notice that neutrinos can also be used to know the sources of cosmic rays. But in this talk, I just want to skip due to the limited length of this talk. Anyway, how shall we detect these very high energy gamma rays? Well, if a gamma ray comes to the atmosphere of the Earth, then they produce really large number of electrons and positrons. We call this as electromagnetic shower. Then these electrons and positrons produce Cherenkov photons. And these photons are detected by telescope. That is the way we observe very high energy gamma rays. In fact, we have already a substantial instrument to observe these high energy gamma rays. This is one of the examples, and this is the, so you can see two very large telescopes. These are the dedicated telescopes for gamma rays. Now, I said that maybe supernova remnants are the sources of the cosmic rays. And in fact, this is the X-ray image of the 1,000 years ago supernova. Now, if we observe this object with extremely high energy gamma rays, how the image look like? In fact, we already know that very high energy gamma rays are coming from these supernova remnants. So this is exciting. So we may understand the origin of the cosmic rays or origin of the high energy phenomena in the universe. So world community is working hard to understand the high energy phenomena by observing gamma rays. And this is the list of the, maybe the partial list of the astronomical objects to be studied with gamma rays. Well, I already explained supernova remnants. In addition, pulsars could accelerate particles, or super heavy black holes at the center of any galaxy might be the source of high energy gamma rays. Or we know that gamma ray burst could be the source of the high energy gamma rays. And finally, if our current understanding is correct, or if our current expectation is right, gamma rays could be observed from the dark matter annihilation. So we think that the high energy gamma ray is a very important tool to understand the phenomena in the universe. Therefore, people are thinking to improve our instrument so that we understand the high energy phenomena much better than now. In fact, the world community has been thinking to generate the substantial observatory for the high energy gamma rays. This project is called CTA, Cherenkov Telescope Array. And CTA will be constructed in both North and the South Hemisphere by a collaboration of about 1,300 scientists from 33 countries. And by the way, this image is for the North. So we really expect a substantial achievement in the near future. Now, the third topic is the exploring the universe with gravitational waves. Well, once again, I want to show you the supernova remnant. And we know that at the center of the supernova remnant, there is a pulsar. In fact, if we have an X-ray image, then you can clearly see a pulsar. By the way, we also know that a substantial fraction of the stars are actually binaries. Therefore, we naturally expect that there must be binary neutron stars or even binary black holes. Then what will happen if they exist? Well, about 100 years ago, Albert Einstein predicted gravitational waves based on his theory of general relativity. And say if if a system of binary black hole or binary neutron star exists, then we expect a strong gravitational wave emission from this system. And well, with the emission of gravitational waves, these black holes eventually merge and create a new, heavier black hole. And I would like to show you, in fact, how they could merge. This is the image of the merger of two black holes. And by the way, at the bottom, we plot the expected waveform of gravitational waves. So let me begin. By the way, this minus 0.76 second is the time to the merger. So let's begin. So you can see two black holes. And below that, it shows the formation of the space. Well, okay, they come closer and closer. And, well, now very close, and therefore, yeah, the slow down, video slow down, and here's the merger. Now, a heavier black hole is formed, and you can see the gravitational wave is propagating to the outer space. This is what we expect for the merger of binary black hole. Then the question is, how can we detect these merger of black holes by using gravitational waves? Well, this is the image how we observe gravitational waves from the merger of binary black holes. If a gravitational wave comes to the Earth, then our space gets deformed. For example, if L1 gets, well, if a gravitational wave comes, then L1 gets longer, and at the same time, L2 gets shorter. Therefore, if we have a laser interferometer, then the light intensity changes. Therefore, if we record this light intensity, then that is the observation of the gravitational wave. Okay, that was the principle. And in fact, maybe many of you may remember, last year, on February 11th, there was an announcement of the detection of the gravitational wave by a merger of two black holes. We think this is really a great discovery, and I would like to congratulate the LIGO collaboration who observed this gravitational wave. Well, okay, I want to tell you a little bit about the data from the LIGO observation. Well, the upper two shows the observed data from two interferometers in the LIGO project. Red is the data from the interferometer at Hanford, and the blue one is the another data from the interferometer at Livingston, Louisiana. And you can see these two are quite similar, and also you notice that these data are quite in good agreement with the simulation. And from this data, LIGO and Virgo collaboration concluded that two black holes of 36 solar mass and 29 solar mass merged at the distance of 1.3 billion light years, newly forming a 62 solar mass black hole. These data told us that way. By the way, you can easily calculate 36 plus 29 is 65. But the newly formed black hole mass is 62 solar mass. That means 3 solar mass disappeared during this merger. And 3 solar mass equivalent energy was converted to the energy of gravitational wave and propagated to the universe. So, essentially in less than 1 second, 3 solar mass disappeared and converted to the energy. So this is definitely the most violent phenomena we ever observed. By the way, this is the LIGO interferometers. So it's a big instrument. The arm lengths are 4 kilometers. And these two interferometers observe that signal. Since this gravitational wave is believed to be so important in the high-energy astrophysics community, there are, in fact, many projects going on in addition to the LIGO project. In Europe, there is a Virgo project whose size is quite similar to the LIGO interferometer. In addition, there is a GEO interferometer in Germany. This is slightly small. In addition, in Japan, we have Kagura interferometer that is under construction. And finally, in India, LIGO India was approved. So there are a lot of projects going on, but maybe you may ask why you need such large number of interferometers in order to observe gravitational waves. Well, my answer is we would like to do astronomy with gravitational waves. Now, in order to do astronomy, you have to tell the other astronomers where is the source of the gravitational waves. But unfortunately, each interferometer has essentially no directionality. They get no directional information. They get the directional information only if they combine the data with the other interferometers. Now, if we have 2 LIGO detectors in United States and Virgo detector in Italy, then the sky localization accuracy is like this. So at some sources, for some sources, the sky localization is reasonably good. However, for some other sources, the sky localization is unfortunately no good. With such a large uncertainty, astronomers cannot watch the merger of the neutron stars, for example. Therefore, we really have to improve the accuracy of the sky localization. And for this, interferometers that are largely separated from the LIGO and Virgo interferometers are very important. Therefore, the Kagura interferometer in Japan and LIGO India interferometer are very important. And if we have these 2 interferometers in operation, then the sky localization would improve that way. And at that stage, astronomers can seriously make the follow-up observation. So that is what we are thinking. Now, in the remaining time, I would like to briefly introduce our activity in Japan. That is the Kagura gravitational wave interferometer. And Kagura is, I think, a unique interferometer because the Kagura interferometer is constructed underground Kamioka. That way, we expect a substantial reduction of the seismic noise, maybe 2 orders of magnitude compared with the surface interferometers. In addition, eventually, the interferometer sensitivity could be limited by thermal noise of a mirror. Therefore, we decided to use cryogenic technology. That means the mirrors will be kept to an extremely low temperature, around 20 Kelvin. That way, the thermal noise will be reduced, and we'd like to achieve a very high sensitivity. Now, the Kagura interferometer is under construction. This is a slightly old photo. This is the beam tube of the Kagura 3 kilometer by 3 kilometer interferometer. The connection and the leak test of the 3 kilometer by 3 kilometer beam tube have been finished in February 2015. And after that, we have been concentrating in the construction of the interferometer. And I just want to show you just 2 examples. Well, one is the central room. We are working hard in order to install the vibration isolation system and the mirrors. But unfortunately, well, this photo is not so appealing because, well, we have to construct the interferometer in an extremely clean environment. Therefore, everything is covered by the clean booth. Therefore, this may not be so appealing. And the right one shows the test suspension of a cryogenic mirror. Well, this mirror is 23 kilogram heavy, and this mirror is suspended by a sapphire fiber. By the way, this mirror is also sapphire. Anyway, we plan the first interferometer operation with the cryogenic mirrors in the spring of next year, and we hope to have a high sensitivity operation in 2019 or 2020. By the way, well, in many parts of this talk, main topic was the supernova explosion. So I just want to mention about the possibility to observe supernova explosion in gravitational waves and neutrinos. If a supernova happens at the center of the Milky Way, we should observe very clear gravitational wave and neutrino signals. And that way, we definitely would like to understand the detailed mechanism of the supernova explosion. And finally, sometime later, this supernova should be observed by gamma rays. But unfortunately, this sometime later is maybe 1,000 years later. Okay, anyway. In this talk, I talked about the so-called multi-messenger astronomy, neutrinos, gamma rays, and gravitational waves. And I believe new messengers will tell us the secrets of the universe. So please stay tuned. That's all. Thank you very much.
Thank you very much, Professor Kajita. Certainly, we'll be staying tuned. And thanks to the wonderful talks by two distinguished lecturers, we are ending the session on time. And thank you very much again to Professor Kajita and Dr. Lucy Jones. Thank you very much.